Right, let's see work on this example. At the beginning of the compression process of an air standard diesel cycle operating with a compression ratio of 18, that means R equal to 18, the temperature is 300 K and the pressure is 0.1 megapascal. That means the beginning of the compression cycle. So the beginning of the compression cycle, temperature is 300, pressure is 0.1 megapascal. The cutoff ratio, the RC, equal to 2. Then determine part A, the temperature and pressure at the end of each process of the cycle. So we have 4 processes, 4 points. So at all the points we need to calculate the temperature and the pressure. The thermal efficiency neta value, the mean effective pressure in megapascal, and the mean effective pressure. Then we have given R value equal to 0.287, right? So the assumptions. So assumptions are the air standard assumptions are applicable. So these are the air standard assumptions, right? Below you can read that out. Then the next assumption, kinetic and potential energy changes are negligible. Specific heats are assumed constant at their ambient temperature value. So these are the assumptions we normally referring when we are working this kind of example, right? Now let's work on the example. So right, let's draw the diagram. So we have PV diagram and the TS diagram. Now if we mark the 4 process, so we started from the 1. We have isentropic compression process, right, 1 to 2. So where the air is compressed in the compression stroke, right, compressed. Then 2 to 3 we have constant pressure heat addition where the fuel is injected and burned. And then we have 3 to 4 isentropic expansion process, right? Then 4 to 1 constant volume heat rejection process, right? So we have Q out here, right? Q out, and we have Q in here, right? Q in. Okay. Then this is where the work in, and we have work out from here to there, right? Both are work out. 2 to 3 and 3 to 4, right? Okay. And the same way in here. So this isentropic compression, the S is constant compression process, and constant pressure heat addition process, then isentropic expansion process, and constant volume heat rejection process, right? So pressure is constant pressure heat addition, in here constant volume heat rejection, right? This Q in, right? Q in here, and this Q out. Okay. Right. So we have given pressure at 0.1 equal to 0.1 megapascal. Volume we don't know, the temperature is given, right? So let's start from, the first part is to find all the pressure and temperature values at all the points. So already we know the P1 and T1 is given in the example, right? Then we have to figure out 2, 3 and 4. So let's first consider the process 1 and 2, right? So from the table we can refer the air tables to find out the U1 value, right? So if we look on the values, so we are interested in ideal gas properties of air, right? And our temperature is 300. So this is the line we are interested in, okay, right? So H value is 300.19, right? But in 1 we are not interested in H value, we are interested in U value. So the U1 is 214.07, right? So that is there 214.07, and the VR1, right, 621.2, right? So VR value 621.2, right? Now if you look in carefully, VR is a dimensionless, right? There's no unit there, right? That means it is a relative value, right? We will talk about more in later on in this one. So VR1 is a relative, that's why the R is there, it is relative value, okay? And so the VR1 is 621.2. Then for the process 1 to 2 we can apply V2 divided by V1 should equal to VR2 divided by VR1, that is the compression ratio, right? So we can formulate this one using the compression ratio. Therefore we can find the VR2 equals to 621.2 divided by 18, so that become 34.51, right? So that means VR2 relative pressure at point 2 equal 34.51. So then we can refer the table to figure out where this point is, 34.51, right? So we are looking at this one, this line, VR1 line, then we get somewhere in here 34, right? 34.51. So we have here 34.51, this one, between these two, 36.61 and 34.31. So it should be in between this one. Therefore we can get that value, temperature 880 and 900, and also the U value, sorry, the H value, we are interested in H value, right? 910 and 932, right? So we can extract these values, right? These are the temperature, enthalpy, and entropy, both are there, okay? Internal energy and enthalpy, okay? So so we can get the X value here, calculate for the fraction X, then X become 0.086. So with that fraction we can calculate the temperature as well as the enthalpy, right? So the temperature become 898.2 and enthalpy 930.98, right? So we have calculated the point 2, then we can move on to point 3, right? And yes, so up to now we have calculated the point 2 temperature value, enthalpy value, right? Then we need to calculate the pressure as well, right? So for that we can substitute the value for ideal gas equation, PV equal to MRT, right? So the point 1 and point 2, if we divide both equation, P1 V1 equal to M1 R T1 divided by P2 V2 equals to M2. Again M is constant, therefore M's cancel out, therefore we left with this kind of equation, P1 V1 over P2 V2 equal to T1 over T2. So you can use that equation, and V1 over V2 we know it is 18 because it is the compression ratio. So with that you can substitute the value for this one, then we can calculate for the P2 value, right? So all the others are known, P1 known, right? V1 V2 ratio known, T1 and T2 both are known, therefore we can calculate for the P2 value, right? So pressure at point 2 and temperature at point 2 is calculated. So okay, then we can move on to process 2 and 3, right? So the process 2 and 3 is constant pressure heat addition process, right? Again it's given as RC, that means V3 divided by V2 equal to 2, right? Okay, then since it is a constant pressure, we know P3 should be equal to P2, therefore P3 equal to P2 equal 5.39 constant pressure heat addition, and also we known that V3 divided by V2 equal to 2, right? Therefore same way we can apply what we call ideal gas equation, and then it become V3 divided by V2 equal to T3 divided by T2. So with that we can find T3 value, all the others are known, V3 divided by V2 is known, RC, and T3 is known, therefore we can find T3 equal to 1796.6 Kelvin, okay? Then we can refer this value, like this temperature values, and refer to the table, find out where this value is, right? 1796, right? Then if we refer to the table, right, so we are interested in calculating the temperature value 1700, right? So it's 1796, so 1796, so it should be in between this one, right? We have 1750 and 1800, So our value should be in between this one. Therefore, we are extracting these two lines, right? This line, values from this line as well as the values from this line. Then we can calculate the fraction. So H3 and VR3 values are extracted. Then we can calculate for the fraction x become 0.932 and also H3 become 1999.1 kilopascal per kilogram. Then also we can calculate the VR3 values as well, equal to 4.0168. Right? Since we know VR3, right, again we can formulate using the compression ratio. Now we can formulate something like this, right? VR4 divided by VR3 equal to V4 divided by V3, and again we can incorporate V2 between this one, right? V4 divided by V3 again multiplied by V2. So you can calculate this one, we have the same expression here, right? Then this one become right. So then VR4, we can calculate for VR4 equal to V4 divide V4 into V2 divided by V2 V3 into VR3. Right? Then also we can refer that V4 equal to V1, right? The same volume, right? That means the volume at the bottom dead center, right? Therefore we can formulate something like this, right? R over RC, right? So V1 over V2 become R, right? Then V2 over V3 become 1 over RC, right? That is what is in here. Therefore then we can find VR4 equal to 18 over 2 into 4.0168, right? Then VR4 we can calculate 36.1519. Right? So the next thing is figure out where this value is, right? 36.1512. We refer out the tables. So we are looking into VR 36. So we have in here, right, 36. Our value 36.61. So we have the exact value, right, 36.61, right? Sorry, we are using 36.15, right? 36.15. I think this is wrong, right? This should be 15, not 51, right? So there's a mistake. I think this should be 36.15, not 51, right? So you can correct that one in your calculation, right? So 36.15. So 36.15 is between this value and this value, right? Therefore you can formulate this equation and find out the fraction, right? Please correct this one when you are doing calculation, right? It's not 36.51, it should be 36.15, right? And then you can figure out what is the fraction here, right? So with that you can calculate the T4 as well as the U4, right? Then you can again apply ideal gas law, right? Then you can formulate for the process 1 to 4, P4 over V4 equal to which is equal to T4 divided by P1 V1 equal to T1, right? So with that you can find the P4 equal to V1 over T4 over T1. Then you can substitute the value, the P4 become 0.29, right? So up to now we have find out all the temperatures and pressure values at point 1, 2, 3 and 4. Then the next part is the neta, calculate the neta. So we can substitute for the neta, right? 1 minus Q out divided by Q in. So the Q out is U4 minus U1, right? So if we go and see, Q out is here, right? U4 minus U1, then Q in is H3 minus H2, right? That is what is here, right? Here, okay? Then we can substitute this value, then the neta becomes 0.578. So now normally you may get slightly different values because I have done a mistake there, therefore you will get slightly different value compared to this one. Okay, so that's it, neta is okay. Then the last part, mean effective pressure. Now what is the mean effective pressure, right? Okay, so what is mean effective pressure is if you consider constant pressure, right? Basically what is asking, what is the constant pressure that gives equal amount of work output, right? So you know we have a piston which oscillate between top dead center and the bottom dead center. So there's a delta V when the piston moves from top dead center to bottom dead center. There's a delta V, change of volume. Then basically what is the value for the pressure? Let's say P mean, P MEP, let's say P NP MEP. So the net amount of work should equal to P MEP multiplied by the delta V. So that is what is asking there. Okay, right? So let's see, for the point 1 we can apply the ideal gas law, PV equals to MRT, right? So P is known, it's given as 0.1 megapascal, right? The V is the one that we are not known, we are unknown, right? That means the volume, right? We can find out the VR value. The VR value is different. The V value, V means the actual volume, right? VR means a relative volume, right? So we can find the V value using this equation. So the V equals to M is 1 because we are applying all the values, P value and all the values for a physical, that means for a 1 kilogram of mass, right? Therefore M become 1, right? R is given as the R equal to 0.287 in the data, right? Then temperature is 300. Therefore we get V equal to 0.861 meters per kilogram, right? Now that's why the per kilogram is come, yeah, per kilogram. That's why it's become 1 here. Per kilogram volume is this much. Okay. Then MEP, network output divided by delta V. Now the network output we can calculate using H3 minus H2, right? Sorry, using Q in minus Q out. Q in minus Q out is the network output, and the Q in is H3 minus H2, the minus Q out U4 minus U1, right? Then it becomes 617.9 kilojoule per kilogram, right? Now the both quantities, right? Delta V, right? We calculate delta V, so we calculate the V value per kilogram and also the network also in the per kilogram, right? Then we can apply delta V. We can calculate the delta V, right? Delta V is the change of volume. So V1 is known, we have calculated that one, and the V2 should be 1 upon 18 into 0.861 because we have known V1 divided by V2 equal 18. Therefore we can consider that one here and find the delta V value as 0.8132. Okay. Right, so delta V become 0.8132. Then we can apply for the mean effective pressure, right? So the work output is 617.9 divided by delta V, which is this one, 0.8132. Then it's become 759.83 kilopascal, right? Pressure value. So that's it. And okay, thank you. We will wrap up the session.